All I'm going to do is to go through the probability calculation again a bit more carefully, right? So that, again, the question there is, it's a probabilistic match. You want to know how often could you have a false positive, right? So the fingerprints match, but the strings don't match, right? Because the way we use these fingerprint algorithms is that once the fingerprint algorithm tells us there is a match, then we end up doing a full match. Okay, just like we said, how do we do one way in which we use Bloom filter? Well, if Bloom filter says it's there, well, then we go to the main thing to actually verify. Right, the same way here. If if your fingerprint says that there is a match, you're going to go and do the more expensive linear time check, and so you want to know, you want to minimize the probability that the fingerprint will say the fingerprints will match, right? And then again, that's what we are trying to do. And remember that the way we were computing a fingerprint is using this method, right? So using this formula, essentially we think of a string as a polynomial, right? And what we are doing here is the x here, right? So we are thinking of So remember what we are doing is we have this string, right? And we take each element of the string as if it's a coefficient in a polynomial, right? And then we evaluate this polynomial at some randomly chosen point, right? And that is this x, right? We are going to evaluate this polynomial at a randomly chosen value x, and that is our fingerprint, okay? So remember that. And so we want to know, okay, what's the probability of false match? Okay, false match occurs if the polynomial, right, you have two different patterns, P1 and P2, and then you evaluate the fingerprint on them, and they happen to be the same. Okay, that's when you have a false positive, right? So again, P1 and P2, I'm saying that okay, P1 and P2 are not identical, but the polynomials match. So we can say okay, P1 equal to P2, and we do the arithmetic, and then we say okay, some polynomial P3 of x, where x is of this polynomial is of degree n, right? Because we said n here, remember, is the length of the string, right? So we have n elements in the string, and therefore we interpret each element in the string as a coefficient. So we have basically an n or n minus 1 degree polynomial. Okay. So if we set P3 of x equal to 0, then if we were evaluating this polynomial over the field of real numbers, we know that it has n minus 1 roots. But as it turns out that even when we evaluate it over a field defined by modulo arithmetic with respect to a prime number, right? So this prime number q is actually, remember in the Rabin-Karp algorithm, we choose a prime number, and we choose that as all the computation is done using modular arithmetic with respect to that prime number, right? And as it turns out that when you evaluate polynomials over this field, once again you still have the result that there can be only n minus 1 roots, which means that the value P3 of x or P1 and P2 are going to match exactly at n minus 1 points, right? It cannot match in more than n minus 1 points, okay? And so the probability of false match is going to be n minus 1 by q, right? Because when you do arithmetic modulo q, the result can be one of q values, right? And of those, only n minus 1 are going to result in a false match, right? So if you take, again, sometimes we don't understand, we should try to substitute real numbers to see what it means. So for instance, for a very long string, n might be 1,000 or even a million, right? But q will be 2 to the power 32 or 2 to the power 64 typically, right? So it's going to be Q is going to be far larger than n minus 1, right? Because your Q is going to be, you're going to choose a large Q, right? Your only limit with Q is that it should fit within, whatever is your word size, right? Because you're going to do arithmetic and you don't want overflows to happen even before you get to Q. So your Q should be, smaller than your word size, but Q can still be very large as compared to n. And so this probability of a false match is extremely small. Okay? So that tells you, okay, so you can keep this probability of false match to maybe 1 in 1,000 to maybe 1 in a trillion, depending upon what is n, and how big is your word size. And so this algorithm makes sense. And once again, notice that this particular result about n minus 1 by q is not really dependent upon a particular choice of p1 and p2, right? So no matter what p1 and p2 are, they are going to only match at n minus 1 points. Okay, and that is ensured by the fact that we choose x to be random and q to be random and so on, and all of those give us the guarantee that in fact with a very, very that the probability of false match is going to be very low. Okay, so that was, as I said, it's a familiar algorithm. All I wanted to go over again was to simply rework some of the probabilities that we had actually looked at before, but maybe not in the same amount of detail. Okay, so the third algorithm that we're going to talk about in the probabilistic techniques is